Now we're in chapter 5.7, and we're still talking about inverse trig functions, but now we want to talk about integrals of inverse trig functions. So remember, in our previous notes, we talked about derivatives of those 6 inverse trig functions, and if we go back to looking at these patterns, I may or may not have pointed this out, but they basically come in pairs, right? So arc sine and arc cosine are almost the same thing, but arc cosine is negative. Arc tangent and arc cotangent are almost the same thing, but arc cotangent is negative. And then arc cosecant and arc secant are, again, almost the same thing, but negative. So the values with c in front have the negative derivatives. And that was the same as our original trig functions. Cosine, cosecant, and cotangent all had negative derivatives there too. So remember, we don't really need to memorize all 6. The most common are arc sine and arc tangent, although it is handy to know at least that they come in pairs. Okay, so back to our notes. Excuse me, back to our notes here. So they fall into 3 pairs, and again, we have the negative partners like arc sine and arc cosine. Arc sine of x instead of u is just 1, because that would be u prime, over square root of a squared minus x squared, or 1 minus x squared. And arc cosine is negative, that same derivative. So with integrals, we can just learn one of the pair. So we'll learn the integral that gives us arc tangent, the integral that gives us arc sine, and the integral that gives us arc secant. Excuse me. And then we'll know if we have negatives of these. If this were negative, that would be arc cotangent. If this were negative, that would be arc cosine. And if this were negative, it would be arc cosecant. Just like previously on the AP test, it's usually arc tangent that you're going to see, and maybe you'll see an arc sine. The rest of these are pretty obscure. All right, so, and on all of these, remember, a squared is a constant. So a squared is usually something like 1 or 4 or 9 or something like that. U squared is the variable. Arctangent is by far the most popular, so again, we'll see that over and over, especially in the homework. So here's an example. You have the integral of dx over square root of 4 minus x squared. I like to organize. What do I have? So a is the square root of 4, which is 2. U is just x, because that's x squared. So du would just be dx. Du dx would be 1, but I kind of like to write that like this. So really I have the integral of 1 over square root of a squared minus u squared du. And as I memorize these, it'll get a little easier, but if you look at that, that is the derivative for arc sine of u over a plus c. So this is equal to arc sine of u over a, so x over 2, plus c. So it's really just about memorizing these 3 kind of formulas. If there's no square root, it's an arctangent, basically. So, all right, so on this one, a squared is 2. A would be square root of 2, and it's never plus or minus. We're always going to make it positive. U would be the square root of 9x squared, so 3x. Du dx would be 3, or du is 3 dx. Either way, I have a little adjustment I need to make. I need a 3 right here, so I'm going to put a 1/3 out in front. So I have 1/3 times the integral of 1 over a squared plus u squared du. I like to rewrite this every time. I've been doing this for a while now. In our notes, like I always write the u sub, even though it seems like you could probably skip that step, especially for these arctangent problems, because arctangent and arcsecant have this extra little 1 over a coefficient, and it's easy to forget about that, or to forget that you have a 1/3 out here if you don't write this out. So this is 1/3 times 1 over a times arctangent of u over a plus c, because this is an indefinite integral. And I can clean that up a little bit. This is 1 over 3 radical 2. Arctangent of 3x over radical 2 plus c. No need to rationalize or any of that stuff. All right, for number 3, a is the square root of 9. U is the square root of 25x squared. Du dx would be 5. So du is 5 dx. So if we need a 5 multiplied in here, we'll put a 1/5 out in front. So 1/5 times the integral of 1 over a squared plus u squared du. So that's arctangent. This is 1/5 times 1 over a, 1/3, arctangent of u over a, 5x over 3, plus c. So that's 1/15 times the arctangent. Remember, arctangent is also written, all of these are also written like this. So, and they use both notations on the AP test. So just recognize that that's equivalent. 1/15 arctangent of 5x over 3 plus c. If f prime of x equals arc sine of 2x to the third, and, oh, we need our calculator for this one, and f of 0 equals 0.5718, find f of 1/2. So I know f of 0, I have a derivative, I want to find f of 1/2. So as my calculator fires up, what I would show if this were a calculator problem on the AP test is that I'm going to do f of 0 plus the integral from 0 to 1/2, because that's where I want to get, of f prime of 0. Maybe instead of f prime, though, I'll write arc sine of 2x to the third dx, and that will equal f of 1/2. So if this is a calculator problem on the AP test, this is really all you have to write. And then I go over to my calculator to type everything in. So f of 0 is 0.5718 plus math 9, the integral from 0 to 1/2. Remember, to type in arc sine, you're doing second sine. That notation is the same as arc sine of 2x to the third dx. This is the final answer because I've already added it to f of 0. So about 0.603. That's about equal to f of 1/2. All right. Determine whether or not you can find the integral using present techniques. If yes, describe how you would evaluate or show the steps to evaluate. So we may not integrate the entire thing, but we'll set up the u sub if possible. All right, so how do we decide if we can do this or not? If it kind of looks like one of the trig integrals, then you would say, well, what's u and what's a? And let's go back and look at our trig integrals. In our previous examples, we were always arctan or arcsine, arctangent or arcsine. Here we have this 1 over u times square root of u squared minus a squared. So let's see if that matches. 1 over u times square root of u squared minus a squared. Yeah, so I think that if we say u is x and a is 1 and du dx would be 1, or du is the same as dx, then this would be the integral of 1 over u square root of u squared minus a squared du. And that's equal to 1 over a arcsecant u over a plus c. Okay, so that's equal to 1 over 1 times arcsecant of absolute value of u over a plus c. And we could simplify that. All right, so can we do a? Yes. What about b? Let's see. This does not, it's not in the form of one of our trig integrals, right? Because if we have an x on the outside, it needs to be down here, so that's not going to work. What about regular u sub? So your next step is to just try regular u sub and try it with whatever is the nested function, the inner function. So let's try u equals x squared minus 1. Then du dx would equal 2x. I have x dx. If I needed 2, then I put a 1/2 out here. So this could be rewritten as 1/2 times the integral of 1 over square root of u du. And we can do that. That would be 1/2. I'm not going to do all the u sub, but I'm going to integrate. This is u to the negative 1/2. So when you add 1 to that, you get u to the 1/2 divided by 1/2. So times 2 u to the 1/2 plus c. So yep, we can do B. All right, what about our next one? Anytime I see square root of a difference of squares, I'm thinking trig, inverse trig. Let's go back and look. 1 over the square root of, we need it to be a squared minus u squared. So, go back and look at this. We don't have a squared minus u squared. We have u squared minus a squared. And the problem with that is like, well, sure, we could factor out a negative, but it would be a negative underneath a square root, and that's no good because that's imaginary. So this is not inverse trig. Let's just make a note. Not inverse trig because it needs to be in the exact setup there. And if it's going to be u squared minus a squared, like this one, it's got to have like an x down here. U sub isn't going to work because if you let u equal x squared minus 1, then again, your du dx is going to be 2x, and you don't even have an x up here. You can't divide by 1 over 2x. So no u sub. So right now, we're stuck on this one. We can't do C because our only tricks so far are u sub and inverse trig, and it's neither one of those. What about part D? Let's see. We have, this is definitely not inverse trig, right? So now we're dealing with our last 3 are natural log x ones. So when we have an x and a natural log x in a denominator, it's best to let u equal the natural log of x because du dx is 1 over x. So du is dx over x, which we have. That is du. So this is the integral of 1 over u du. And we can integrate that. It's the natural log of the absolute value of u plus c. This is one of those natural log of x problems. If we just have a plain natural log of x, I think we talked about this in our notes a day or two ago, we can't do anything because u is natural log x, du dx is 1 over x, but there is no x here to speak of, so we can't do E, not yet. And then finally, let's see. Now, in the previous problem, we said let u equal natural log of x, and du is 1 over x dx. So we can use that same process, right? Even though natural log of x is in the numerator, we're still allowed to do that. This integral comes out to be the integral of u du, and that's just u squared over 2 plus c. And then we could go from there. All right, so we're kind of getting to a point where we have all these different ways to integrate and ways to take derivatives, and we're starting to kind of run through all the functions. So at this point, it's really about practice and knowing how to experiment and use all of your methods. You might not pick the right method to start. When you get stuck, you have to start over and pick a different u, basically.